Testing, testing. That's what. That's what.
Testing, testing. I think it just needs to be like reconnected or something.
Wow. Yeah, I can hear now. Testing. Okay. We're back.
All right, so I guess we have plenty to say now. So a recap of what we tried to explain. Hey, Nick. Perfect.
Thanks,
Excellent.
everyone.
Thank you. So I guess we might as well start from the beginning again. So the objective today is to lay out the. I'll even show you this. The objective today is to lay out the components in a nice, fashionable manner on the car. To solder all of the remaining connections to the motors. To test all 4 of the motors forward, backward, and try a PWM script on each of the motors to make sure that they're actually operating correctly. And then lastly, we're going to actually start moving into the math behind the rotational, the rotational structure of the Mobius mechanism wheels. So which wheel has to go forward when another wheel is going in reverse to get a certain direction, and how accurate we can make those angles. So that'll be an interesting adventure, and for that portion, we're definitely going to want some help from the crowd, from a hypothetical and mathematical perspective, to try and get a decent visualization of what we're looking to accomplish. Just a quick reminder that all of this is new to us as well as you guys, so it's a learning experience for everybody in the room. So what I'm trying to accomplish right now is basically we're going to disconnect all of these connections on the RC car. So I'm just drawing a quick little schematic to make sure that we can actually install it back properly to recreate the environment that we're in right now. Sure. So we have a connection from the battery to the positive terminal block, a connection from the battery, connection from the battery to the negative terminal block, and then all of those connections go to our drive, go to our second drive, and then go to our buck converter. So that's our power circuit. We also have, I suppose that's basically everything that we have to recreate. And then we have our connection from our buck converter to our Raspberry Pi, which is just micro USB.
And that's we will not be doing that for most development because we don't want to be using the battery all the time, right? So this is actually going to be coming from our house's power, but then grounded with the battery to not have the problem that we had in the last stream.
Yeah, so I don't know if any of you were at the end of the last stream, but we were actually seeing some pretty significant issues. We were trying to drive, using the Raspberry Pi, we were trying to control the motor drivers, but we weren't getting the voltage out of the Raspberry Pi that we were expecting. And what we were actually seeing is a floating voltage. So the voltage was fluctuating between 2 volts and 4 volts, which wasn't enough to act as a binary 1 to drive the wheels. And the reason for that was basically we had 2 separate grounds. The Raspberry Pi was connected to a USB, which was connected to an outlet. And since it was connected to an outlet, it had a different ground. It had a different ground than the battery. We didn't have a common reference. So what we had to do is either connect the Raspberry Pi to the buck converter like we have here, or a second option would be to bring the negative voltage from the battery and just tie it into the Raspberry Pi, into the ground port of the Raspberry Pi's general purpose input and output pins. And we can go further into that. It's pretty, grounding in general, in my opinion, is a pretty complicated topic. I definitely struggle with it. But what I do know about grounding is you need to have common potentials between common items, because that is your reference point. That is your quote-unquote 0 volts, even though voltage is just a relative term. Anyway, nonetheless, let's start taking this car apart.
We have a question from Nacho Katie before we get started. What is a buck converter?
Oh, we'll show you. Alright, we're still zoomed in.
Sorry, I'm still getting used to this camera. Alright, so it's this piece right here. And we're using it to convert from these 12 volts that are coming from the battery in and we're coming out with 5 volts that is required to power the Raspberry Pi over here. And we have 2 options. We have 5 volts coming out of these pins, or we have the USB, and that's what we'll be using. So you can just plug it right in, and that's the buck converter.
Yep.
Anything else you want to add to this?
No, that's about all. Buck converter is basically a sort of a digital transformer. Yeah, it was and it's actually this specific buck converter is a very nice chip, very well constructed.
Natural Kitty says so kind of like a mini transformer.
Yeah, exactly. Kind of like a mini transformer.
Not the robot in disguise kind of.
So we're just gonna take everything apart for the most part.
This is why we can't have nice things, is because we take them all apart.
Yeah, everything was put together as like a testing environment, but now that we actually want to configure it on the car, we need to reorient it and basically just adjust the wire lengths and make everything nice and tidy. Called it. Yeah, exactly. You did call it. You know what's up.
You've been paying attention. Must have been the previous lessons.
The previous lessons, exactly. There's a lot of learning.
So there's a pop quiz down this, right?
Pop quiz.
Oh wait, I mean, we didn't say anything.
Yeah, that's not very pop-like.
So you don't just accidentally pull things loose. Yeah, I thought we could just rip it right off, but you know, apparently we have to use screwdrivers.
Apparently. Did you ever see that video?
It's
It's some like 3 or 4 year old. It's a TikTok. It's some 3 or 4 year old, and he's getting interviewed, and he just keeps saying apparently. It's like apparently. I don't know. I don't even know how to quote it, but it's hilarious. I find it hilarious. Okay, so let's get rid of this.
All right, Nacho Katie's gonna leave before the pop quiz.
Yeah, that's valid.
You're gonna love it.
I don't know if you guys knew this, but we are using Velcro as our connector for all of our components, so we'll actually be able to move them around on the car. I think it was a pretty decent purchase. Velcro, I definitely recommend Velcro for temporary mounting.
Where's the end of this?
It's in there. It's in there somewhere.
Oh gosh.
Okay. So you have to put some consideration. If you have any recommendations for how we're going to lay this out, I would very much appreciate it. This is definitely not my strong suit. Organization is the least of my skill set.
Well, Nacho Kitty.
Just so you don't pull things loose. Just so you don't pull things loose. Oh, we're modifying everything just to make sure that everything kind of fits nicely. So we're going to try and lay things out so that everything's nice and, I guess, a cleaner installation. I'm assuming that that's what she was asking. Okay.
Yeah, so cleaner install, going to be easier to debug and show you how everything works. And it's fun to use Velcro.
It's fun to use Velcro. Pretty nice. Okay, so considerations. We need wires to come through the bottom from the motors. We need. Do we want to solder them first, or do we want to do the wire? Do we want to bring all the wires up?
Yeah, I think that would be good, especially if there's nothing on it right now.
Yeah, maybe that's a good opportunity.
We know that we need those ends, and these ends are even put on anything.
So let's start, because these things have to come up as well. So this wire that's sticking up here is actually the wire for the built-in wheel encoders on the motors.
Ooh, that's very cool.
Which is nice. We don't quite know how to interface with them yet, but we'll try to be reasonably straightforward.
Do you have something to connect to this end?
We'll use some nail headers.
Okay. It looks like we only have one of those two.
Well, that's a bunch of bots. Okay, so let's start playing around with some solder.
Alright, soldering time. So we have the solder itself, soldering iron, and how long, what about these ends? Is this what you plan on using?
Yes. Do you want me to solder? We can solder a little bit on big camera, and then you can start looking
I'll
into
give it a shot.
Oh, sure. Absolutely. Are you going first?
How do you remind me how it's done?
Sure.
Yeah,
Just
just so the audience gets a good example. Yeah, I'm gonna get an extension for it.
Sure.
If you have one here, actually.
Get messy. It's messy. Yeah, so they both Nacho Kitty and Nick recommend we talk about something.
Yeah. Does anyone have any questions we should talk about, or any ideas? Any other interests you think you want to kind of shoot the shit with us?
As someone might say, shoot the shit. Yeah, it sounds like a me thing.
It does sound like
Oh, Lucasism.
You want to talk about Lucasisms?
What interests people? What about hydraulics? We all know I can go on a rant about hydraulics or wind power or solar power.
We were just talking about solar and battery packs. Kind of the interesting stuff there. I think solar is pretty exciting.
Solar is pretty exciting. I don't know a ton about solar technology, but I do.
This should be on now.
I guess we could chat about solar energy for a little bit. So, solar and that's heating up, is it?
Yeah, I don't know what it goes with. Just take it there.
Yeah, sure.
Should we put it on the paper or what?
That's what it is. Yeah. Make the hot on the paper.
This is one thing self-solve. Okay.
Yeah, that's fine. Going to that's okay. This is heating up now.
Sure, should be.
Cool. This. Just let it drop. Just let it slip. Yo.
Alright.
Alright. No, it's singing.
I like it.
Yeah, so I guess we could talk about solar panels for a little bit. Well, I don't really know what to
Let's talk about hydraulics. You love
talk about hydraulics. I don't know what to say about anything right now. I usually know so many things.
Well, how hydraulics is inferior to electricity, I think is what your usual point is.
So okay, yeah, let's talk. While this is heating up, let's talk about hydraulics.
Do we want to go over here with the face? Or are you
I'm using the paper.
using the paper? All right, paper it is.
Just in time. I think you mentioned it before, but what sort of sensors are you going to have on the car? Okay, yeah, that's it. Love a good solar panel. Yeah, let's talk about the sensors. That's a good idea. Actually, I think I'll let Glavin talk about that a little bit.
Do we actually have the ultrasonic sensor here? I don't think
There's
so.
good chances in the box.
Might be in the box. So the ultrasonic sensor we'd like to add, that's just measuring distance. Things like radar, what a bat might do, it's just going to send off some kind of pulse and get the response and then measure the timing difference. And from that, we know the speed of sound. In this case, we're able to say this is how far it traveled because we know how fast it is and we know how long between. Thanks for drawing it. Yeah, that's exactly it. So we know how fast sound travels. So we know based on the time delay between sending out the transmission and the time we actually receive that transmission. You can say this is the difference in time, and this is actually the distance that sound traveled before it reached us. So it's a really inexpensive way for us to detect where obstacles are and things like walls. So that's one thing we want to put on the front, and we've used in the past is the ultrasonic sensor. Other things is the camera, which is over here. Excuse me. So everyone knows what the camera is, but this is pretty exciting because we're going to be able to put it right on the Pi and stream pretty decent video and actually process this. So we could essentially build a self-driving car that uses video input, process that with machine learning, different techniques like from the library OpenCV, and we could say, oh, where is Lucas? Let's detect where he is and let's have the car go follow him. Or probably more fun ideas if we can come up with them. So I think there's a lot of potential here. Let's see, what else are we going to be adding? I think if anyone else has suggestions on what to add, we have quite a lot of pins. Any suggestions there, Nick, or welcome to Wizard, Wizrad, please? Oh, Nacho Kitty, don't tease me like that. Oh, I think Nacho Kitty wanted to hear more about the solar panels or about hydro.
About hydro. Yeah, let's talk about.
Wizrad loves a good solar panel. I also love good solar panels.
Oh,
I'm getting solar panels in my house, so I'm very, very excited about them.
Wizrad could probably talk about solar panels a little bit better than we could. But we were talking about hydraulics. Now, when you think of a generator, you think of rotational motion. So a generator is basically you have an object inside a magnetic field and it rotates. And as it rotates, it outputs current through wires in the simplest form. So as it's outputting this current actually comes out since they're basically 36 or 1800 RPM motor with 4 poles, which means 4 magnets in a sense, and then 2 receiving points. You end up getting a 60 hertz signal. Basically, so when you come out of the math behind basically the rotation at 800 RPM over 4 poles, you get 60 hertz, which means 60 cycles happen per second. So you get this rotational energy, and you see it in the form of a sine wave as it comes through the wire, which means you have your 0 volts, 0 energy. You have your positive, and you have your negative over time. So in a sense, a sine wave, if you were to imagine a sine wave in 3D, it's actually a spiral because it's going positive and negative, but over time. So you can imagine that it's actually spiraling. So it's a rotational motion over time. Point is, hydraulics, you have to consider the fact, or hydraulics are different because they're actually a transfer of linear energy. So if you have a piston or a pinion of some sort, and you have a linear force, you can push linear force. Oh, I'm inside the screen, aren't I?
Yeah, hold that. As you can see it.
So you have a pinion, you put a force in this direction, you can have a linear force pushed through a tube, a hydraulic line. It's interesting because it's linear force converted into linear force, or transmitted through linear force, versus electricity is sort of circular force transmitted in a form of circular energy. And usually AC power, upon reception, ends up as a motor. If you want to be the most efficient release of energy, you release it as a motor. So generate, transmit, and then motor. Whereas this linear motion, basically, you can transmit it and you can push something down along somewhere far away. You can push something. The only problem with the linear motion that is hydraulics is it's very challenging to make continuous linear motion. Like, for example, if you dropped a rock off the top of a hill, and that rock landed on the piston, and then it started falling, the piston started depressing, eventually it would have to come to an end. Whereas the rotational energy never really has to come to an end as long as you have an energy supply. You'd have to put energy back into the piston system to get it to restart. Anyway, back to the soldering. I'm sure this is hot enough by now.
Okay. So we have a couple questions here. Are you guys concerned with the wheels spinning at different speeds, causing the car to drift as it moves? And that's actually a feature, not a bug. And that's what we're really excited about with these wheels. So for anyone who's not familiar, we'll just quickly show you. But each of these wheels have rollers on them, along with turning. But you notice they don't turn like cars do with these mechanical wheels. So they actually are going to drift via these rollers. And that's where the math comes in, is trying to figure out how much we want them to drift such that the overall body is moving in the direction that we want. So there's going to be cases where we have certain wheels moving forwards and others moving backwards, but the end result is the whole body either rotates or goes in this direction. So we're going to be able to take advantage of that drift from these individual wheels. So it's pretty cool.
And hopefully the wheel encoders, if we ever have a situation where the wheel is going faster or slower than we expect, hopefully the wheel encoders will allow us to adjust the throttling through a PWM. So if we expect the wheel to be moving at 1 rotation per second, for example, that's probably pretty fast, but 1 rotation per second, and we see that the wheel is only rotating at 0.9 rotations per second, we can throttle it up and hopefully counteract it. We are using motor drivers. So these motor drivers do have some capacitors and some voltage regulators within them. So what that'll do is basically, if we have any decay in voltage, hopefully the voltage regulator outputs a proper voltage to the motor, making a consistent motor drive for the duration of the life of the battery. I'm sure we'll see some issues as the battery depletes, but hopefully not as bad as the robot car in school.
And Not Your Kitty is another question. Once you guys get the car moving, you should train in, or actually maybe more statement my question, you should train an algorithm in OpenCV for tracking a particular object and getting the car to chase it. And yeah, that's pretty much the plan. Is we really want to incorporate not just hardware, not just software, but have the full scope of what we can do here. So using OpenCV, using the camera, maybe creating it to have different games we could play with it. But we want to try to maximize and really test ourselves on all these different fronts, from both electrical, software, and diving deep into the hardware. So I think having it chase an object is a good goal that demonstrates that we're able to utilize each of these different phases, each of these different levels. So that's pretty exciting for someone like me who has never done the hardware stuff, or even have never done the CV piece. That's gonna be really interesting to try something completely new. So I think we'll have a lot of fun with that together. Particular object, yeah, such as a cat or chili, maybe. Yeah, and even avoiding objects is a big one. And one of the original visions we had is actually installing 2 cameras. So as everyone I imagine knows, is we as humans have 2 eyes, and that's really great for sensing depth. Computers are not really good at sensing depth, and there are different techniques you can use by putting in 2 cameras, and it gives the computer a little bit of an advantage to catch up. It's still not as good as a human, but it's definitely better than having 1 camera. Unfortunately, we only have 1 port that we can plug the camera into, so that plan quickly evaporated. So right now we're going to be looking into other approaches which take a single video and image feed, and from that single image are able to infer a depth map. So that won't be as accurate, but hopefully it's going to be enough that we can see if objects are close or far away, and potentially at a better resolution than the ultrasonic sensor that we spoke about earlier. Because we worked with the ultrasonic sensor in the past and found that if you have it at the right angle, when we transmit that signal going out, it hits the object at an angle and actually just goes off into the abyss. We don't receive enough of this back such that we can accurately measure the distance. In some cases, it was saying, well, there's nothing in front of you, even though there was, so our previous car just ran into the wall. So that's definitely a bug, not a feature that we want to try to avoid.
Curious if Nick's experiences would be able to help us with those problems.
Yeah, that'd be great if anyone has a particular solution for that. I think navigation is going to be a big piece, making sure it doesn't run into things. All right, so we're going to solder these pieces. So we've already soldered one of the motors, so we know it works, and now we're just going to do it for the other 3. Any other ideas for different sensors we can add, or other tasks that we could try to do with the sensors that are going to be attached? In line with what Nick was talking about earlier, about the drifting as it moves, I am curious to see if we can make it look like it's drifting, like you see Fast and Furious. You make it look like it's drifting, even though these tires are, in a certain way, going to have a different level of control. Versus when you watch like Fast and Furious or all these other racing movies, you're seeing them intentionally lose traction. I'm expecting that this is going to have a fair amount of traction, but we might be able to still see some pretty cool motions, given we can control it to rotate and move in different directions. We're going to have a lot more flexibility. So it's going to be neat to see what we can do with it. The WizRad, the 3DS uses 2 cameras to do some 3D stuff. Yeah, exactly. Yeah, so that's the kind of things that would be really interesting. And maybe there's a way in the future that we can get 2 cameras, because that was something I was really excited about. And I've read about it, but I have not tried it before. And if we can get 2 cameras hooked up, I think there's a lot of really interesting things we could try out that are going to be pretty difficult with just one. There's a lot of products outside. I think the Microsoft Kinect was probably one of the first consumer products that utilized this approach. where they had a camera array, a microphone array, and a bunch of different implementations like this that use multiple sources to help kind of understand spatially how things are working. So a camera array, multiple cameras that is really great at trying to sense depth and object recognition, things like this. So it was really advantageous for the Microsoft Kinect for gaming, because you could have a bunch of people in the same room, and rather than just trying to recognize where the bodies are, they could have a lot better understanding of where they were in the entire room. So when you're playing, I haven't really played it very much, but let's say there's some kind of tennis game, and you're moving back and forth, it's able to know, how far away you are and your positioning there. Shortest path problem would be cool to solve. Would probably involve a higher up camera. Yeah, and that'd be really interesting if we could train it in a similar way to like a Roomba or the modern smart robots that for vacuuming. If we could have it navigate around, track with the camera what objects are available, and then actually remember this for later. So that the next time it goes out, we say, okay, use your memory. Now create a path. Recognize that there's a door here, and there's not a door here, and there's an object in your way. What would be a way to get from point A to point B? And that's going to be a lot more difficult than it sounds, because even just saying, oh great, I can create a depth map from an image, which is a very difficult challenge, but also to create a 3D model from that depth map is actually really difficult. Just because I know relative to where I am, where things are, I can't necessarily say if I move around that I can create some 3D model. That's still a very difficult computation. Now, I think someone else proposed in another call was to actually use the LiDAR sensor on, say, my iPhone, for example. And LiDAR is really exciting because it does create a really good idea of the depth map. So if we could, say, hook up the phone and use that as the front-facing camera and it navigate it around, there's other software that might be able to help us create a model. And then that model we could use to create a shortest path algorithm in the 3D space, similar to what these robot vacuums are using today. So that'd be pretty cool. It's very involved, definitely not easy, but I think it'd be a lot of fun and demonstrate what some of these real projects, like not just these robot vacuums, are actually doing. It's going to be a lot harder than a lot of people could imagine, but a lot of fun for sure. All right, how's the software go there?
First one was tricky. The first wire was very tricky. It's pretty tight to get inside. It's pretty tight to get inside this location inside there. So I struggled a little bit. It seems to be a solid connection. Might have to touch it up in the future. That's okay. Wasn't my best work, I'll tell you that.
For those that didn't join us the last time when we were soldering, can you talk about the importance of having the solid connection?
Yeah, so when you're soldering, at least my limited understanding of soldering, you should always make sure that you're actually heating up the metals that are connecting to each other. So in this case, the copper wire and the aluminum terminal on the motor. You should heat up the metals and not the solder itself. And the reason for that is basically if you heat up the solder on its own, the solder will melt, but it won't connect to anything because the metal won't be able to make it melt. So it won't actually mate with the metal. Instead, it'll just sort of fall off and blow, which I actually experienced just now. So this little piece, I'll try and get it out. Yeah. This little piece of solder right here, what happened was basically I didn't heat the metal enough and I touched the solder on the tip of the soldering iron. So the solder softened, but then it couldn't actually connect to the terminal, so it just fell off as a solid piece of solder. Interesting enough. We're in a situation right now. It doesn't make a huge difference at these low voltages, but if we're on like medium to high voltage scale, we would see that over time, an aluminum to a copper connection without any sort of anti-oxidizing agent, you would end up seeing basically an oxidized layer between the copper and the aluminum because of the gradient in resistance between the two objects. So you'd have a point of resistance, and over time it would cause the copper to oxidize, and when the copper oxidizes, you'd end up getting an oxidized layer. And the problem with that over time is is you actually lose conductivity, and eventually it'll become an open circuit between the 2 points. It's not a big issue from our scale because we're not pushing a lot of energy through these connections, and we're also not talking about years or tens of years. We're talking about at the most 2 years. Even 5 years or 10 years would be okay. There was an interesting joke that was going around once upon a time. It was an aeronautical joke, and it was basically the Americans spent $1 million on a pen that could write upside down, and then the Russians came in and said, "Oh, we'll just use a pencil." Now the thing was, the internet made a big joke about the fact that the Americans spent $1 million on this pen that could write upside down in the not upside down, but right in space, in the vacuum of space, because you don't have the pressure on the end of the ink cartridge. But nonetheless, the internet made a huge joke that like Americans overcomplicated the issue. But the actual issue was that graphite from pencils is a conductive material, and in space, you lose that conductive material in floating within your cabin. And if that conductive graphite ever finds its way into an electrical component while you're in space, you could have a catastrophic failure. So pencils were not the solution. It's just an interesting little side piece. Did you ever hear that one, Bob?
I have not. That's actually really cool. My understanding of people in space as well is that they have people tracking in and out if you were to use objects. You just imagine every time you need said pencil, you could tell someone way away on planet Earth and say, "Hey guys, I need to use this pencil." And they're like, "All right, I'll check it out with so and so." It's like the most complicated library book or Blockbuster renting of a thing, but I guess the stakes are so much higher. You have to do it.
Yeah. You lose a pencil in your spacecraft, and that pencil finds its way into your main computer and short circuits something that makes it so you can't come home.
Yeah. It's incredible. I still don't understand fully how they can monitor so much space junk. Like that's what blows my mind. It's, like we know there's a ton up there. What do we? And unfortunately, there's a lot of space. But how do you monitor something like that, consistently, and given the sizes that they're doing so?
Because even a small object, like a pencil, moving at a high velocity,
is going to make a huge big hole in your ship. So it's incredible that we can stay up there.
I guess space is huge, but realistically, in our immediate orbit, it's pretty cluttered. You ever see those pictures online of the clutter?
Of the clutter?
I don't know if they're renders or if they're just renders or if they're actual some kind of pictures from some sort of telescope. I'm not sure.
Yeah, I haven't.
Yeah, I think I've seen what you're referring to, but I think they're renders because they often make it look a lot bigger.
Yeah, true.
Yeah.
Now that I think about it, it's been a while since I've seen one, but yeah, that makes sense.
Yeah, because I imagine if it was as big as the pictures that I've seen, they'd be looking out their window at the space station saying, "You know what, guys, maybe we should come home."
Yeah, this is dangerous. So Nick, you asked what sort of sensors we'd be using. Do you have any ideas what kind of sensors would be interesting to put on this? I mean, we could talk about infrared. We could talk about putting infrared location sensors. We could talk about putting what do you call it?
Infrared would be neat.
Infrared would be neat. We could do some light sensing, so some light frequency sensors, which would be cool for like object recognition. So you could have like an infrared light, and then have an infrared receiver on the car, and the car hunts for an invisible light to the human eye, which would be neat. That'd be cool. But I was thinking about the 6-degree freedom chip, with an accelerometer, gyroscope, or 9-degree freedom. Accelerometer, gyroscope, barometric pressure sensor. What else is on there? Magnetometer. Magnetometer.
I just pronounced it poorly. Yeah, you were thinking of that. I think it would be a lot of fun to have that on there.
Yeah. What would we use it for?
Well, like we were talking about earlier, when Nick talked about the drifting. Is that the aircraft?
No. Anyway, keep going.
We're talking about the drifting. Okay, one moment, not your Katie. I'll let you speak your idea about it in a second. Yeah, we were talking about the drifting, and I think there's an interesting opportunity if you have enough sensors in the car to teach it how to drive in unconventional ways. And I don't think it was Google or one of these other companies, but I know it's a self-driving car company doing research into actually making this car drift. And they had this kind of figure eight looking track. And of course you say, okay, go around here, don't hit any objects, drive the path that we chose. But it wasn't as simple as that. It was do it, but while drifting. Do it like you're one of those guys in the movies. And the way they're able to do these kind of things is by having so many sensors on it, they're able to see that the weight shifting around and that you're in the optimal performance for that drift. And I think, of course, with our mechanical wheels, it's going to be difficult to do something to that extent. From a hardware standpoint and also software, it's a really difficult thing that they were trying to do. But it made for a really interesting video. And I think having some sensors would make it that we could build an autonomous car that has a better connection with its body. So it's not just looking and seeing this window to the reality in front of it, but actually sensing different things. Like if we hit it into something, or poke it, or pick it up, it can react in different ways. So like let's say it's driving until you pick it up, that's something as well. Or maybe it's trying to learn about, like I said, if it is drifting, it's trying to learn how, let's say we didn't hook up a wheel encoder, we said how could we teach it to learn based on the accelerometer and gyroscope and sensors like this, how can we use those very inaccurate sensors to get the same information we would from a wheel encoder and demonstrate the wheel encoder is a lot more accurate, but we can actually use that relationship and demonstrate both of them, which is pretty neat. And in other cases, you might not have a wheel encoder, so that's why that research is particularly interesting, because you can, in the same way Elon Musk doesn't want to put LiDAR on Teslas because they're very expensive, and he's very confident that if we can solve a hard problem using computer vision on a low-cost camera, that's a harder thing to do because you don't have all that great depth map data and things like this. But if you do it, you solve all problems, and I think that's a great way of looking at it. Is let's solve the hard problems. It's going to take a lot more upfront, but once you do it, you just open up a huge opportunity in the future. So not your kitty. I have an idea, and I don't know how to implement it. Voice sensors. I bet these are some open source libraries to comprehend voice sounds and commands. Yeah, we could definitely do voice. Funny enough, I was just saying this to Lucas earlier. So, I don't know, a few years ago, I went and got a blue snowball. So that's this guy here. So a blue snowball for audio, and that's just simple microphone. And my objective was actually to hook this up to a very, very old Raspberry Pi. And this was before all of these Alexas and Google Homes and Apple HomePods. And I wanted to build my own home automation, of course, inspired by Iron Man, Tony Stark with his Jarvis for his home automation. I wanted something similar. Now I didn't end up finishing it, but there are a lot of projects out there, even at the time many years ago, and there's even more now. Natural language processing and speech recognition are really, really popular, pretty much in everyone's mobile phone and a lot of different devices in their household now. And we could stream the audio over the Raspberry Pi's Wi-Fi, for example, and with probably not too bad latency, get the response and then process those commands. And a lot of these algorithms that they have, like in AWS, which is Amazon Web Services, or on Google's equivalent cloud, and these other solutions, they're supporting streaming. So it's not just take this audio file and do it with the full audio file in hand. It's actually, I'm giving it to you millisecond by millisecond, and I need that response as soon as possible. The same way you have your phone, it's as soon as it recognizes your voice and it turns on, it's streaming it live. That's why as soon as you finish your sentence, it already has the answer, because it's not waiting for it to finish to process the whole thing. It's trying to do that as quick as possible. And that is now something that is offered to other people like ourselves as developers. So we could definitely connect this with voice recognition and go build it into the car. So you could say, hey car, go get me a glass of water, and it could drive over to the fridge, and maybe we add an arm, maybe we just have a coaster on the top that people could put stuff on. That's definitely within the realm of possibility. And that actually ties back to your point earlier about shortest path problem and trying to solve it. If we can model a 3D space that is, say, an apartment or a house, and say, all right, here's your floor plan,
you are here right now. I need you to get me a drink. So voice recognition goes in, take the voice command, process that in real time, very, very quick, in the cloud, and then execute that command. We'll do pathfinding. Even the pathfinding itself could be in the cloud. Right? We're thinking about it's pretty decent, the processor on these Raspberry Pis, but it might not be as powerful as something in the cloud. So you picture something like Amazon or other companies trying to do delivery services with a drone. You don't necessarily want to have the entire planet on your Raspberry Pi, but if you said, hey, offload it to cloud servers, you could say, I have a drone at point A, and I want it to go to point B, and it could solve that in the cloud, do all the expensive computation, and then just execute. And all you send back from the servers to the Raspberry Pi, in this case, would just be, hey, do these actions, very explicit, and still get that incredible response time. So I think that's pretty cool. I think that's definitely where we could work on this. And especially if you put a robotic arm. I've been wanting to build a robotic arm for a while. Help me convince Lucas to do so. That'd be great.
Yeah, robotic arm is in the future. What do you guys think of building? If we were to build a set of remote controlled boats that have laser transmitters and receivers, so that we could basically have a laser tag fight on the water that disables the boat whenever the boat gets shot for a specific amount of time, and then once it gets shot X amount of times, you lose the fight.
Lasers equals good. All right, we got one upvote so far.
Nice.
You want to try?
Yeah, I will give it a shot. I would buy that. Yeah, I saw. I over the past few months, I've been particularly interested in watching these kind of videos of people building cool projects. And there's been some online. People have built like boats, cars, and some bigger, some small. Like one was a car that you could actually fit yourself into. And it was a car / boat. It was like a boat hull with a boat motor behind it, and it had big wheels, so it could actually drive on land. So he just drove it right from the beach, right into the water, and then drove off. And that was a pretty big project, as you can imagine. But it's just amazing. These people are taking it on by storm and just say, no problem, I can solve all those issues. Or they buy an RC car, or in one case it was a fire truck. They bought a fire truck that had no motor, and then bought an RC car that had the motors, and then made a Frankenstein's monster. They put them together, and we're now able to have a remote control fire truck. And then to top it off, we talked about remote control arm. They put an arm on top of it that spewed out fire. It would spew out some kind of liquid, probably propane or something, or that's gas, but it would spew something out that would ignite, and it would actually spew out fire. And they drove it around and lit things on fire. And probably don't try that at home, but it's still really impressive to see what people are building.
You can switch
I'm hardware face cam.
your home face. Very good.
Figured you had enough staring at the car. Maybe you'd rather stare at me for a minute. Probably not. I changed my mind. They don't. They wouldn't rather.
All right, what am I doing here again? So I need to solder.
The ground wire on that third motor.
Ground is green and that is negative. Okay.
And you're gonna want to aim it. I was thinking of aiming it through that hole right there.
Through that hole over here. Okay.
Yeah. See how I'm kind of like aiming them through all these.
That's case as always.
Best view so far, huh?
Okay. All right, so this hole here. I wish you guys could have a better view of this.
Yeah, that's a tough one. You can just keep. Here, maybe while he's doing that, I'm gonna put you on the small.
Yeah. Make me smaller.
There, and I'm gonna use. Which screen should I be using for Google?
It's the one at the bottom.
The one.
Should be.
This one.
Yeah, good job.
Cool.
Hopefully. Yeah, there we go. It thinks it works. That's all we need.
Sweet. All right, so we're gonna start while he's soldering away. We're gonna start googling around, trying to figure out.
Just want to make sure you get a good window. Got so many tabs. Open up. Very good.
Cool. Thank you. We're gonna start googling around about the Mobius Buchanan wheels.
Best view so far. Very
That's
good.
me.
There you're
That's
talking.
me. I'm the best view. $318.
Huh?
What? Okay. Math. Let's go as simple as possible. Math. How to do it.
You said we type.
How can drives work? You'll need JavaScript for this.
That's good. I can translate. What we need is to find the math.
Yeah.
I don't even care if it's in Fortran or if it's in Brainfuck, you get extra points.
In Brainfuck.
If you could find someone who coded this in Brainfuck, I will be extremely impressed. For all those who are not familiar with Brainfuck, please look up that language, spelled like it sounds, one word.
Alright, before you can get to telling the wheels, you have to know which direction the robot needs to go. So this guy's describing what you described, which is one.
I think I'm gonna suck at this.
Nacho Kitty said she'll do brain fuck consulting.
For a price. What price, Nacho Kitty? We'll pay you in nachos. You can be a guest speaker. We'll have a limited supply of nachos. We'll keep it coming. Don't worry. The other proposal was actually writing it in Doge script. If anyone else has seen Doge script, I definitely recommend taking a look. It is real, and we could absolutely write a production-ready product with Doge.
Let's take a look at Doge script.
Yeah, you should actually take a look at Doge. People will understand it even if they're not familiar with it. Please look at this.
Wow, so syntax, very Doge.
So what's great about Doge is the Doge script will transpile, which is like essentially convert. So it will convert from Doge script to JavaScript. So most websites right now and other production apps are built with JavaScript. So you can write something in Doge, compile it to JavaScript, and submit that and use it for a production thing. We can 100% write our RC car in Doge.
True Doge implements true Doge mode, which splits line by 3 spaces instead
Such
of
production, wow.
a string of Doge. Such iota
and-
much end.
Nachos and paying for all the smart lighting. Oh, you know what? We should have an episode on smart lighting. I could show off my own theater at some point.
Yeah, really.
That'd be good fun.
That would be
I
fun.
want to add some more lights before that. If we're gonna have to dress to impress.
What is this stuff?
Are you excited about Doge script?
Sure. Sure.
All right, so we need votes on what language you should write in. What is holding you back? What is holding us back?
The more complicated a language gets, the more Glavin has to do without me.
This is true. Also, I haven't figured out how to get this thing to stick. So in
The more
terms of
complicated the wire gets, the more I have to help Glavin.
yeah, I almost poked my eye out right there. So yeah, that's how my day's going.
Marianne votes white space.
I know what's great about whitespace is we could do it in Doge and in whitespace. Like that's my favorite thing. Is we could have the second piece of code in the whitespace of the Doge script file. It's incredible. I've never tried it. I've heard some really great examples, but I think it'll be a lot of fun. You wrote nothing when showing the code on stream. Yeah, exactly. I can't imagine what editor you need to have to be able to write in whitespace productively. I don't know. People are more impressive than that.
That's all right, Nick. Thanks so much for stopping in. We appreciate it. And if you have any questions, just fire the questions along to me, and I'll try and answer them if I can.
Thanks very much, Nick, for joining. I hope I'm doing this right.
I hope you are too. Oh, here we go. Analyzing the mechanism wheels. For your direction, use trig to find the angle the joystick was pointed.
Oh, Nick as well. There's a way you can watch it later. This is all recorded.
He's watched a few.
Okay, good. Excellent.
What you're after is the angle the joystick is pointed. To do this, you can calculate inverse tan of y over x. You'll need to compensate for angles outside of the principal branch, between negative pi over 2 and pi over 2.
Oh, that makes sense.
I'm glad you found one in plain English.
And this will be tough, but it's got nice drawings.
Yeah, I think the drawing is the best part. What's cool is if we can learn how to do it, we can have a visualizer. Maybe they help us debug. So I don't like blow my hands off.
Oh dang! Did you see this website? Let's go.
There's a drag and drop. Oh, hey, that's what I want. Click and drag.
Wait, click and drag left, right. I'm very confused. Oh, that changes this. Oh, dang! It has the. Did you see what it's doing? You got like.
Now you're talking.
So this will show us everything.
So that's it. That's what I want. Well, I love it.
That's a perfect visual.
All right, maybe you should follow this so we can get this thing done with, because I'm struggling.
Sure.
Yeah, you can go look at that stuff. I suck. Okay, so 1 second. I want to get like one. So like I heat this part up. I got my loopy loop.
Yes.
In here. Does that look decent?
Yeah.
Is it not tight enough for you?
No, I'm just helping him not your kitty. You don't want your butt to the camera.
White space plus plus might help.
Can you imagine the C++ and white space hybrid? Just pain.
Wow, this is cool. Click and drag left and right. Oh, left and right.
What should you put on this?
One of them I did poorly.
We'll make that too.
No, you did this one.
I'm gonna say we. We are better. Has anyone else seen Venom? Venom the movie. Oh wow, it's actually sticking there.
I haven't seen Venom.
You watch movies.
Really?
Who else watches movies? Anyone in the chat? Oh, I got stuck. I don't know if I'm doing this right. Don't try this out, please.
I'm just stuck playing with this little graphic.
Oh man, oh no.
Can you double check this?
Yeah, you're like, I'll take it.
Alright, check what I got.
Oh, you did it?
Well, in theory. I think it looks like shape. Stay. Remind me to get a holder for this. And where do I put this?
Hi everyone, I get to play with toys now. Oh, this is a neat. It looks good? Don't lie to me.
It's not great. Good enough though.
Alright,
Worse than I did the first time.
soldering is a little bit hard. Yo. Oh, I can't see the Oh yeah, you're saying yo to me. Thanks. Yo. Alright, so let's take a look at this code here. Interesting. Yeah, so as we spoke about earlier, each of these Mecanum wheels have rollers. So that's going to allow some give. So it's effectively, they all, my understanding is they move in 45 degrees, like they're effective force. So we're trying to get it so that the forces, where we have it, so we have our right, yeah, I have a camera. So we have our right angle, 45 degrees is where each of those wheels are working. We want those components to add up such that if we want to go right, we're moving the appropriate wheels that they're 45 degrees kind of line up to push in this direction. And I think there's probably an example here, I'm sure. Let's see. So if I want to go right, I'm going to put this right here. Good. So you can see this front left wheel is going what appears to be forward. Same with the back right. And then the front right is going in reverse and the back left in reverse. Yeah, so the end result of this force is, the majority of the forces are going sideways, and then the vertical forces, the forward and backward, actually cancel each other out, making 0. So that's the general idea. So we're trying to just line up these forces to make them to go in the direction that we want. Wow, this is a very, very cool site. Front right gradients. Yeah, this is going to be a little bit slow for us getting started, but I'm very excited about this. Push to drag. Very cool. Yeah, so I would think here, the magnitude is what we want it to be in the end, in terms of the actual speed the car's moving. But the y and the x are more likely what we have to work with, right? Like I said, we don't really get to say this wheel, this wheel in particular, move at this angle. We can only go forward and reverse, but we know that it's at 45 degrees, so there's going to be some amount of y and amount of x that it will contribute to for the overall body of the car. Here we go. Yeah.
Why did not your kitty say yep?
I think it's because I joined. I sat in front of the camera. Yeah. Just friendly and awesome. You're gonna get tons of nachos when you come over and guest speaker with us and do some open CV and brainfuck. Yeah. Okay, now this is on GitHub, which is particularly exciting because maybe we're able to utilize this code. That is interesting. So CMasters. Actually, no, I wonder, does this link go to the website or I'll just Google it. That's convenient. Yeah, this is very convenient. So I think this is the GitHub for CMonsters 2605.
Competition bot.
Very cool. We could compete with our bot once we're done.
Yeah, once we steal all the code.
Oh, interesting. It's actually an organization. Yeah, there we go. I found the... No, I did not. What? I was trying to look for their code, actually. Sketches and stuff. Bev. Interesting. So this site here, I was trying to see if I could find their source code for this. I found that website, but I don't think that's exactly what I want. All right, one idea. Lurking for a few minutes, FYI. Okay, cool, thank you. Okay, so I think I found, it was under archive. Okay, so we now have some code. So we can actually clone this. And let's open it up, and let's see what they were doing, because this is really interesting. So they have a bunch of really interesting examples here. Great diagrams. I think this is particularly interesting because that's actually what we want. We want to be able to, oh, there's a G to show graph. Oh, wow. Have you seen the graph mode?
This is what I was looking at.
Oh my god. Yeah, so this is exactly the kind of stuff we want. So I have now forked this code. We can now clone it.
Oh, I get it. Electrical. It's just a power factor.
It's just a power factor. Bam.
The difference is the power factor.
Dang. And yeah, so there we go. So this is really cool. I think it's exactly what we need. Are you excited?
I'm very excited.
Sweet, man.
Cool. So I guess that's our main reference. Save that page.
I have. I
Favorite
forked
it.
it.
Put it right on your desktop.
Forked it. All right. So what we're gonna do is we're gonna pull this down locally so we can inspect the code itself. And I think that's gonna be pretty telling. I'm gonna make this text a little bit bigger for everyone. Okay.
You should when
sure.
you should comment on their code, like when you look at it, whether it's well written or not.
Yeah. Well, even if we find anything to change, we can suggest something.
I just even mean that. Just mean even like syntax, clarity of writing, just general practice. Because I don't know a lot about coding, right? I know how to hack,
I see. Yeah.
hack a thing together, but I want to know more about like how to write good code, professional grade
Well,
code.
let's take a look. I think that's interesting. Can. Okay, so what I just did there, we cloned we forked their project, so we just have a safe copy of it. It's open source anyways. It's available on GitHub. We have cloned it locally with Git. We're not going to talk a lot about Git, but essentially the idea is it's used for production, able to make a distributed team of software developers collaborate and work on a single piece of code. And so it's something that's being used for this project, and I've now pulled down their project code, and we're able to actually view it. So let's take a look. So here is an MD file, so that's a markdown file, and it's referencing various files here for sketches in Mecanum. Oh, interesting. It might actually be written in processing.
Well, actually, we can definitely compile it.
Oh yeah, no, that's fine. Well, we're gonna rewrite this anyways in Python. I just want to see what it looks like from a logic perspective. So, what section was most exciting to us? Let's take a look. Let's go back here. So if we look here, I'm particularly interested in this diagram, which showed the graph, and you're able to say pick a direction and then get the relative speed, so forward and back, and also the magnitude for those particular wheels. So this is analyzing Mecanum wheels. Okay. So analyzing Mecanum wheels, sweet, and I'm guessing it is actually this JavaScript here, wheel graph. Nice JavaScript. Okay, very cool. Interesting. So let me just try to digest this a little bit. So there's a lot here is revolving around rendering. So actually taking the raw data and rendering it in this form, which is this diagram here. So rendering the chart, rendering the spinning of the wheels. So that's a lot of the code that we're seeing in front of us. Try. Wheel graph. Okay, so here's draw, here's drag, selected value. Yeah, selected value. So you can see here, selected value on mouse drag. So when we are interacting with this code, with this applet, we were dragging the mouse and it was changing some value. So I'm guessing that this mouse drag event changes the selected value, and that selected value is actually our angle. And what's interesting is if you look below, it does have some code that says selected value is greater than, in this case, pi times 2. So we know it's something involving circles because we're seeing the incorporation of pi here. It's probably just trying to limit it so it doesn't go too high or too low. There's a limit on making sure it doesn't go below 0, so there's no negative numbers. So that's just making sure that we as a user don't drag it to something that it can't support. Let's see. So because of that, we can look for all references to this value, selected value. Let's take a look at the first reference here. So it starts off in JavaScript, we define this variable. We initialize it to 0, so that's all fine and dandy. This is where we have the drag event. Okay, I think this is where the action happens. So in the draw, so this is a particular JavaScript function. So it's something that's being called. I don't know how much we want to get into the low-level parts of languages. Like, do we want to talk about like what a function is and things like this, or I think in the general idea is a function.
Yeah, a high level
Yeah.
explanation, but we're going to be writing some more scratch stuff so we can explain it more as we're going.
Yeah, exactly. So it's okay if you don't understand, if you don't have a coding background, if you don't understand it right now. But the general idea is we have this reusable block of code, and you'd refer to that as a function, or in other cases, a method. And we can pass information to it, and it can do different actions. Maybe it processes some calculation. Maybe it moves a wheel. So there's a bunch, or in this case, actually draws an image, and you can see the image being drawn here. So there's, that's just what it is, but reusability and taking input and doing an output or particular actions. So in this case, there's quite a lot of input that it's working with. Wheel movement, a selected value, it's talking about sine. Yeah, so sine minus this, okay. So like you said earlier, it's changing the phase, is what it looks like it might be doing here. Okay, let me just see. Draw Mecanum wheel. So it's recalculating this Mecanum wheel, and okay, here we go. So we have 4 sections here. 1, 2, 3, 4. Each of them are calling this method called draw Mecanum wheel, and it calculates these 2 values. This is wheel 1 movement and wheel 2 movement. And what I'm finding interesting here, and this actually makes a lot of sense, wheel 1, if you're drawing the Mecanum wheel, so whatever motor this one is, and this one is, these 2 wheels are always the same. So they are mirroring each other. And these 2 wheels are also the same, but they are the negative value of wheel movement 2. So if we look back here, we notice the same thing. These 2 blue motors are the same. The 2 red motors are the same. And in this case, the red motors are going in reverse. So let's move it over here. Yes, you can see, yeah, the blue is going forward, red going reverse. If we did this, all of them are going in reverse. If we went over here, yeah, you can see where it's limiting my motion. Not the best way to. Okay, actually, it's easier just to do this. Here we go. So boom. So we see both. So intuitively, all of them are going forward, and this lines up here where we have, let's see, pi divided by 2. So when the selected value is pi divided by 2, and you give, so pi divided by 2 minus 1/4 pi, or plus 1/4 pi, it looks like the y values are the same, or maybe one of them is negative actually. But either way, so then they're all going in the same direction. So that's what the equivalent for forward is. You could see backwards, I'm assuming would be here. Yes, so you can see this is going backwards. So that's interesting. This is a really cool visualization. So actually the brain of the code we want is right here. And actually more specifically, it seems to be right here.
Sine waves.
Yeah, the sine waves. And it's just a matter of shifting them off and then knowing that these wheels should be negative, these wheels should be the same. And if you do this math that's found here, essentially you're good to go.
Grade 11 math.
Grade 11 math.
Great.
Yeah.
I was terrible at that.
Trigonometry actually was a very rough year for me because I just didn't care. But what's interesting is the following year I started my first programming course in high school, and I built this thing called Nerd Fighting, and it was in Java. It was my first year using Java, and I wanted to build out a physics engine. So it was stick figures in a multiplayer game, so you can actually boot up the app here on 2 different computers. It would communicate over the network, and you were able to have a multiplayer game where you had these stick figures that would shoot, and they would have gravity, so they would collide with the floor. They would shoot each other and fall over and collide with the floor. They would get hit by the bullets, and that was a collision model. There were different interactions with their limbs and things like this. So I actually learned more trigonometry in my side project for class, my coding class the following year, because the year prior in trigonometry, it wasn't applicable. But the year following that, I needed to know it for physics and building the simulation. So I thought that was pretty interesting. That really hit home the importance of having a need and then learning to satisfy that need. And that's how I learn the best.
Engineering, you say?
Engineering, say. Yeah. What as we said earlier, and if you can engineer, you can do anything.
If you're good at engineering, you're good at everything.
Yeah. Yeah. So I think
The reference that he's referring to there is from it's from Mark Rober's YouTube page. The first comment on his dartboard video is basically what I learned from this video is if you can engineer, you can do anything. Cleaning this up.
I think it was on this one, but I'm not sure.
It was on the dartboard.
Oh, it was on the dartboard? Oh, the dartboard was hilarious. Highly recommend you take a look at Mark Rober's videos. He is a big inspiration of mine, and it really excites me to work with Lucas and build out some cool stuff. So, all right, so let's take a look here. Lesson learned: if you're good at engineering, you're good at everything. Yeah, so that was something we saw today and really hit home. And yeah, that's why we're doing this. We want to get really good at engineering, and then there's no obstacle. If we want to build some fancy self-driving car with a bunch of cameras and doing some crazy math, and it has lasers because lasers are good, we can make it happen because we're going to learn that engineering side of things. So it's going to be fun. And I love how vast the field of engineering is. You go from software to the hardware to the electrical. There's biological engineering. Actually, that would be a cool thing, is to make a biological computer. We talked about sensors. I would love to do something where we actually hook up some living, like probably a bacteria of some kind, but something that actually is biology related, and connect that and get that interface and see how we're bridging the gap with electrical signals.
Oh, yeah, we can do that.
Yeah.
We could. So, I've probably talked about this before, even on stream. But what we did in our biomedical engineering course.
Yeah, they're storing in DNA now.
Yeah.
Yeah.
It's
Very
wild.
very crazy stuff they're able to do, right?
I'm sure it's not that far out of our realm. We just haven't been exposed to it yet.
Far around, like for us to do something that's biological.
Yeah. I think we just need to figure out how to actually interact with it. But like, for example, in my fourth year of electrical engineering, I took a biomedical engineering class, and in that class we made an EKG, an electrocardiogram, which is basically when you go to the doctor and they hook you up with all these pads and you see your heart rate on the screen, and you see it's like the spikes and valleys. So anyway, what we did was basically use what's called an oscilloscope, which measures electrical activity in an electrical system. But we used it in an oscilloscope and built a circuit that basically allowed us to inject current through our body, current limited though, so that it was low enough that it couldn't hurt us. And we used aluminum chloride pads, which are those pads that they put on your body while you're receiving that electrocardiogram. You put those pads on your body, and it converts electrical energy, which is electrons, into, I guess, fluid electricity, let's call it for lack of a better understanding right now, where they change it into ions, because the electricity in your body is actually ionic flow, not electron flow. So for example, a chlorine negative ion, Cl minus, acts the same as an electron. It's just an ion instead of an electron. It's a piece of a molecule instead of just a singular electron. Anyway, we needed a way to integrate between electricity and ionic flow, and we used it with an aluminum chloride pad. And when you energize that, one of the aluminum molecules releases and starts flowing through your body.
I think that's mine. 1 second.
Anyway, it was a very interesting class.
It's like I should tell my dad I'm in a stream right now.
Come on.
Dad can watch. Yeah, that's really exciting. What's another thing I was thinking about as well? I think often about computer hardware. Actually, I'm not really big into computer hardware, but I find it interesting is people inherently think that us human beings or animals or things like this are very different. And you think about, we're not really computers. I would say that we are a computer. One, because a computer is simply something that processes information, and that's exactly what we do. But to go further is when we first started with computers, we have classical computing using bits. We have new computers that use quantum bits and qubits in a quantum computer. We have our biological inner workings, and that's the same thing, processing information, all with different architecture, with different advantages and disadvantages. Like our brains are actually relatively slow from a connection standpoint versus the speed of electricity or light or something like this that electronics can take advantage of. Versus like quantum technology is really great because you have superposition of these qubit particles. So they're all different approaches to solving information processing. They have pros, they have cons, and what's really exciting for me, I think, for the future is how can we say this particular architecture is good at this kind of problem? That's the one. And the same thing with CPUs and GPUs. No one's going to say I want to run this game only on my CPU. They know GPUs are better suited. And that's the kind of realization that I hope people will get to when we're talking about classical computing, CPUs, GPUs, quantum computers, and then biological computing, whether it be computers or in the future, connecting us with Neuralink and utilizing our computation internally that's a little more creative and can maybe inform the computer to make different decisions than a strictly logical one. So we're going to come up with some interesting stuff. So I think that the relationship, we're complementary in a lot of ways. So it's really interesting to see the future unfold. So very excited about Neuralink and the projects that are similar to that. I don't know if anyone's thought about that a lot, but just an aside.
It's a very interesting topic. Thanks for kind of delving in, and I hope that introduces some questions to the chat. That's an interesting topic that can realistically go on forever.
Yeah, that's for sure. I don't know if you how are you looking over there? Do you want to focus on your screen? I think we're at a point now where, in theory, if this math works out, we're at a stage to write Python code, but I prefer not to shock you. Since you're working over there, and plug stuff in.
Oh, I can plug it in.
Wait, are you sure? Because I love to use the motor, so it's a problem.
Yep. By the time you get a script working, I should.
Oh wow! Or he's ambitious. Okay.
I'll have one motor working.
I'm excited then. All right, you're gonna boot that guy up. Let us take a look. So if anyone remembers our last sessions, we used Balena. Let's see, Balena.
Right now. Pi is energized.
Thank you. Oh my God, I'm not logged in. Give me a second, everyone.
I'm adjusting some of this layout. Trying to clean it up.
I'm just gonna log into everything. Get it all booted.
So just while he's doing that, I'll show you what I'm working on over here. Basically, I've taken away the negative bus and combined both the negative and positive bus into one terminal block so that we can reduce the space required for our power supply. Just because when I tried to lay it out on the car, I didn't know how I was going to do it. So smaller might be easier. So we have our power on the left and our ground on the right. We'll just connect everything. These two for ground and these two for power. Make sense? Let's see. So you've got it up. All back to drawing board? Yeah, I was going to try and use this, but then I started trying to lay this out. It's so wide. Sorry. Yeah, it's a little bit of a perfectionist, but that's okay.
That's what we want. You wouldn't want your engineer at NASA to not be a perfectionist, or your pilot to not be fully coherent.
I applied for NASA once.
Did you really?
I did. A few years ago they were looking for astronauts. I applied.
Astronaut? You applied as an astronaut too?
Yeah,
I thought you applied as an engineer maybe, but...
Space engineer. Astronaut.
Oh, okay. All right. If you can hold a wrench down here, why not over there, right?
That's right.
All right.
Same thing. I'm athletic.
That's very cool. Oh, Nacho Kitty is glad you didn't get in.
What?
I'm sure they have great internet up there. You could have FaceTimed all the time.
Yeah, I figured it was one of those things where it's like, well, I might as well shoot my shot. I'm not going to get in, but...
Oh, he shot a shot already. Oh, are you okay? What are you doing over there?
Ignore that. Maybe I'm not that good with a screwdriver.
Now we're learning why he didn't get into NASA. All right.
Can't even use a screwdriver. Okay.
Okay, let's see.
So where do we want to mount the battery?
1 sec. My stream is just fluctuating. Okay, everyone can still see me. Alright, good. Yeah, it just did something weird, but I think it's still good. Okay. Let us log in. I want to make sure everyone can see this. So I'll have to boot up for a second. So right now it is plugged in. Has power. It has Ethernet. It's wired in, so it's gonna be super fast. And yeah, hopefully he's gonna be ready because we're gonna try to code up a storm very soon. So we're going to SSH into this box. All right, you can ignore what I'm going to do next. This is just specific to Belina, and essentially all I'm doing is just connecting to a little container inside. Oh, I'm hitting my limits, remember. I'm just connected to a little container inside, a little Docker container that. Oh no.
No.
I'm running out of memory.
Oh no. Oh no. That web page is probably a lot of your.
Actually, I wonder. I think Chrome is problematic. I'm going to close out Chrome. All right.
Okay,
Sorry, everyone. Just quick pause.
I don't understand. Where
What cable are you looking for?
fourth one of these.
Telecasts. Oh, our webcam is taking a lot.
You made a bad choice at what? Not taking me to NASA? I don't think I'm competent enough at anything to go work for NASA. I couldn't even be, I don't know, I don't even know what. I couldn't even be at general something.
For 1 sec.
Not even good enough at coming up with jobs that I could do. Maybe I just can't do anything.
What? You can definitely solder really well.
Can I?
Well, it's not bad. We're gonna get the job done. It's gonna be great. And once you're an engineer, you can do anything. Remember that.
Once I'm an engineer, whenever I get there.
Whenever you get there, don't rush it.
Don't rush becoming an engineer. I did rush it. I rushed it as fast. I rushed it as hard as I could.
Did you? Do you think you missed anything on the way there?
Yeah.
Any gaps in your knowledge?
There's a couple gaps.
Oh, someone's just calling for Daddy. All right, I need some channel points to sponsor the special guest. Hi, Max. This is Max. He just hit his daddy button. Because he wanted to come say hi. This is his daddy button. So this means he wants to come say hi to us. Thanks, Max. Yeah, where does that work? You're streaming away. Say hi to everyone. All right. You go see Mom? All right, you can chill around. Don't worry. Special guest? Yeah, hey, guy. Oh, yeah. We're just working. All right, I'm just cleaning up my computer, so please hold. I just need to get it back so it doesn't crash.
Now that I have this all laid out, how do I want to bring it? I think those are going to come up from the side. I'm not going to come up today. I need your opinion, Glenn.
I got plenty of opinions.
I need your opinion.
All right, 1 sec. Let me just sweet. All right, shoot.
So these cables are for the wheel encoders, the pre-installed wheel encoders. I don't know how the best way to bring them through, and I don't really want to bring them through these holes, which would be the only way through the center of the body. So what I'm thinking is literally just, well, because it's going to interfere with our mounting.
So if you want to put something else in the center.
then we can't.
Yeah.
So I'm thinking something on top of it.
So I'm thinking we just quite literally take them down from underneath and come up from the side. In all cases. Just
Well, so what? So I would like it to be as symmetrical as possible for
Sure.
weight distribution. So like
so
how
these
do you-
two come up to the side.
yeah, I think that's fine from a symmetry point of view. I do worry about having them exposed. Like I wouldn't mind putting it here and then the Velcro over top of them. I don't know what the implications of that would be.
So if we come through here, this.
And they did. So they have to connect over to.
They have to connect to the Raspberry Pi, I believe, but like I'm not even really sure how to use them yet. Let alone.
Oh, we have 4 of them too. Oh my gosh.
Yeah, exactly. There's a lot happening. So this would be, this one's in a poor direction, but that's just because whoever mounted this mounted it wrong.
What does it mean?
No, the manufacturer.
Oh,
These
see,
ones-
it is mounted. It is pushing down.
And this one's the same. This one's the same. It's the other direction.
Well, that's odd. There's no one to fix that.
No, because if you switch,
For everyone who can see what we're talking to, what direction these guys.
yeah. So this one specifically sucks. It's gonna cause issues.
Oh my god. Yeah. Dude, what the heck?
Yeah. So I don't really know what to do about that. Unless this is actually removed.
We can rotate it?
You can't do the terminals to it.
So you can't rotate that. Don't know why they would do that. So the screws there.
Right, but the screws, there's only one place that the wheel can go, and that's all the way up. Right, the screws mount the motor, but the motor has an offset wheel. It's not centered. So if you rotate this further, this motor can mount further.
Okay.
Well, so that's an issue. So I mean, it could be as simple as this. Like this solves the problem, taping it down there. Like that. We just put a maybe hot glue to there so that it stays down.
That's your point at the top. So you're thinking the Raspberry Pi goes on the butt end of it?
I'm thinking Raspberry
Or
Pi
that's the
goes
front.
right there. Yeah.
Oh, okay. And the camera.
Or I guess we need the
I
servo.
figured this would go back a little bit, so they'd have some space in it.
But yeah, you see these things, especially because we don't really know what we're going to do with them. I'd rather them come from the sides so that we can have them disconnected for now.
Okay.
Because like
Yeah, I'm okay with the sides considering what this is, as long as we can keep them tight.
yeah, well we can do this. We can bring it like this and tape it down here so that it comes right at the corner and comes over the top. Hollow magneton. No sleeve. Oof. But good.
Thanks, Dr. Katie.
Yeah, so if we tape it on the way around this corner, we tape it there, tape it to the motor, tape it around the edge. I think around the edge is the best way, so that it comes up like this.
Yeah, I'm okay with around the edge. I think it makes sense. It's unfortunate about how they've structured it.
It is unfortunate. I was disappointed the first day,
You,
but I did.
you held it in.
Yeah. Didn't know yet. So I'm gonna disconnect all these coming up this way.
Yep.
Because we don't need them for now. They're messy.
We can do that. Well, now we're stuck, everyone. All right.
was hard to undo.
Oh, I think our video might be frozen.
Oh. Can you still
It's,
hear
it's
us?
still it's still streaming. I'm still getting audio, but 1 second.
We didn't miss anything.
Any chance the phone got disconnected? Interesting. I think we're pushing our camera to its limits.
Of course, we can't get through a whole screen without
Yeah, some kind of issue.
technical issues. Yeah, it's just the camera, it seems. Not the actual screen.
Yeah, I'm not getting any video feed.
So close is right.
It's nice to have a stream without issues once, eh?
Also, beat us for life if you're in the stream. Appreciate you stopping in. You found an Articuno. Is it hollow? Yeah, I see what you mean. I am gonna push this further back. It's gonna be front and center.
This is weird.
Camera. Is there any input to that software?
No anymore.
Man.
At some point to see what happens.
Sure. Software.
All right, there we go. Something is back. It is now rotated properly.
Yeah, face it toward me first.
There we go.
I mean, you're mentioning weight distribution. I really don't think the weight's going to matter, although I'm down to make sure everything's measurable. It's no problem.
Yeah, I just. Especially if we're gonna put some sensors on it later.
Yeah.
Okay, we're almost back.
Okay, so where are we going to sit the battery? Battery underneath?
Oh. I think I have to restart the stream to get the feedback out.
Oh no! Quick restart.